Uh, no,
Is it?
sir. It was like using x raised to n is equal is congruent to x mod p. I saw I proved this, and then you give me problem p combination with np is congruent to m c. Yeah,
Okay, okay, right. So this is a
m.
right. Okay. So was it something this right? This is congruent to PA, PB like this?
P was multiplied this side actually, left hand side. PA combination with PB is
Okay,
congruent to uh,
okay.
the,
Mod P.
congruent to mod. Yes, sir.
But that was the same thing. That was just yeah. Anyways, okay. That's the
Okay.
same thing. Yeah. Okay.
Yes, sir.
Right. So you could not do this. Okay. Uh, yeah, let us think about this. I also don't know how to do it. So we can try it together. Yeah.
Sir,
Huh.
x raised to n is congruent to x mod p. So, we have to prove like a combination with b raised to p is equal to a cb. I was thinking like that.
Right, that is correct. Although your voice is not clear to me. I don't know why. Maybe you're not, maybe you should use earphone or something. I'm not sure.
Yes, sir, I'm using
You're using,
headphone.
okay, then it is fine. We will manage. Yeah, but it's not very clear. Anyways, so this you're saying,
Yes, sir.
okay, all right. This I know, but then what do we do? Let me just check just 1 second if this is correct. Yeah. Okay, I was just checking if there were any conditions. Conditions. Okay, so if we just write, maybe it will come. So PA minus 1 till PA minus PB plus 1, right? By PB factorial, right? So that's what it is. Is this correct? Like, okay, correct meaning that this is equal to PA choose PB, right?
Hello.
Yes, yes, I can hear you. Yeah.
Uh,
So
I
I'm
lost
just,
my connection.
yeah. Yes, so it will just come if you write it. Okay. So I can tell you that, you see, if you just write and arrange, because see, if you have to just compare this expression, right? Is my video on?
Yes,
Right.
sir.
Yes. You have to just compare this expression, which I've circled here, with this expression. Correct?
Okay.
Right? And
P.
you have to, yeah, just simplify it modulo p. So simplify it modulo p means, especially the left hand one, you have to simplify the left hand one, right? Because you see in the numerator, there are PB terms, right? In the denominator, there are PB terms. But here you don't have PB terms. You only have B terms in the numerator and B terms in the denominator. So the simplification must happen on the left one. So that's the general intuition. Means, yeah. Okay, now if I consider this, I go P minus 1 steps back, and then I go P steps back, right? This, and then again I continue the same thing, right? That on PA minus P, I go 1 step back, and on again PA minus P, I go 2 steps back. PA minus P, I go P minus 1 steps back, and then again P steps, and I continue like this, right?
Okay.
Continues like
Okay.
this. Now you see, you can simplify the numerator a lot. Why? Because first of all, these p's that are occurring, this p that is occurring here, and the p that comes here, right? And similarly, the p that comes here, these you can cancel with the p's in the denominator, right? They will come in the same way. So if you forget them, and then you see, this is basically, this is just minus 1 mod p, right? PA minus
Yes.
1 is just minus 1 mod.
Yes, sir.
Okay, so that is the thing. We are simplifying every factor modulo P.
Yes, sir.
Okay, because we know, right, that if X is congruent to Y mod P and Z is congruent to W mod P, then I know that XZ is congruent to YW mod P. Right, that I can,
Yes,
that
sir.
multiplication can happen. So I can simplify on the level of every factor, and then I can give the result. This is something which some you may not have, you may not usually do, but you should start doing, right? That you can just simplify it like
Yes.
anything. Okay, so that's, it's very, very simple. I'm not doing anything. Okay, now you can see in this whole block you can do the same thing, and this block will just become p minus 1 factorial, because the PA in every factor in that block will go away,
Okay, sir.
right? Do you see that, right? And that will minus 1 times minus 2 times minus 3 till minus p minus 1 factorial, which is just p minus 1 factorial because it is minus 1 to the power p minus 1. which also we don't have to worry about because P is at least 3, we are assuming. For P equal to 2, you can do separately. Okay. So you see, it's very, very simple, right? So this block is P minus 1 factorial. Okay. Similarly, this block, well, for the same reasons, right? For the exact same reason, this is also P minus 1 factorial. Tick.
Okay.
Tick, right? It's all the same. And this is basically your A, and this is your A minus 1. This is your A minus 2 because the P's will get cancelled with the denominator piece. Okay. Now you know by Wilson's theorem that this is minus 1 mod P.
Okay.
Okay. Now you can see this is looking a lot like this one. Right? This PA becomes A, and this becomes A minus 1. This is A minus 2. Now you should finish the exercise. You should finish the rest on your own. Okay. I'm not doing it. Okay. And if you get stuck, then you should again ask. Okay. But I think you can do it from here. So this was a purely elementary exercise. This was a purely elementary exercise. There was no issue in this. Okay. But the point was that this is nothing. This is a part of a much stronger result, which is called Wolstenholme's theorem. Okay. This was not the goal of my discussion. The goal of the discussion was for you to get comfortable with fields. Okay. Because you see, when you are in high school or when you do modular arithmetic for the first time, then you treat this mod p as a new kind of thing, right? But later on you see that this mod p operation, right, that addition mod p, multiplication mod p, these satisfy the axioms of a field, right? So you can work with them exactly as you work in field. Okay. So it's good to write this, but also we say that this is equal to this in FP. Right? And we know that the rules in FP is basically modulo Pn. So this is the same thing as that one, right? But we will say like this, okay? But that doesn't matter too much, okay? However, what is interesting, and for that I cannot say FP or anything, is something more. Something more is true, and this is the actual thing, Wolstenholme's. And this, I don't know, you can try it. This is not part of the goal of anything here, okay? This is up to you. If you are interested, you should try it. That this is congruent to, let me just once again check again. Just checking on Wikipedia. So yeah. Yeah. So the result is that this is congruent to mod p cube. Okay. And here p is a prime bigger than equal to 5. Okay. You see, this is a stronger result. Why? This will imply that. Correct?
Okay.
It implies, right? Because this is saying that p cube divides the difference. We had to prove p divides the difference, right? And here it is much more. So this is actually the harder result. Okay. You can read the Wikipedia page of this if you want later on. You can think now also. Yeah, this is a very interesting one, but this is not part of our official discussion, so I will otherwise. But let me just see. I think this is discussed in this algebra book of Dummit and Foote in field theory, but I'm not. Let me just look at it.
Sir, how to check that which condition is more stronger than, I mean, this condition implies that this result is more stronger than other result.
Yes. So you see why I said this result is more stronger than that result, because this result implies that result. Means using this result, you can prove that result.
that result was for any p, and we have here special conditions for p. Then how this is generalized and that?
Okay, yeah, you are correct. Yeah. So in that way, I was wrong, but I meant that for p bigger than 5, at least it implies. For p 2 and 3, it is very simple, right? So we don't like. I was like not assuming that thing. Yeah, you're correct. So it doesn't imply for all cases, but it implies for p bigger than 5, right? Bigger than or equal to 5. You are correct. It is not a generalization in that way, but at least this is true. You agree.
Yes, sir.
Right, that's a P2 and 3 is easy, that you can do, right? That's, I mean, that is easy, that we are not saying. Small primes, it is fine. We can, even Fermat's last theorem, you can prove for 3 maybe easily, or maybe it's not easy. Yeah, but anyway, that's a different, that's not, that the problem is maybe not primes, I don't know, actually. Yeah, I don't know, actually. Okay. Let me just look at this once, I think. Splitting fields. Yeah, 1 minute. I think I found it. You can think, maybe you can try to prove for p square that it is at least mod p square you can prove. Then also it's not a bad thing, right? Even if you can prove
Okay.
mod p square, that also nice thing. Yeah. So these things have many nice properties. <sighs> 45. Sorry, I'm taking a lot of time. Just give me 1 second.
No problem.
Yeah, it is just for my own. Right. No, yeah. So even yeah, as expected. So this is true, and show that the binomial coefficient this is the coefficient of x to the pi in this is correct, and this right. Yeah. So yeah, that was actually the goal of the exercise. So this is fine, but I would like to go back. I would like to go back, and so let's go back to our original question. Okay, we wanted to show this, right? Now you may have thought that the proof that we did right now, that was not in the spirit of what we did earlier, right? A
Yes.
slightly different
Yes.
in nature. You would want a proof which is in the spirit, right? In the spirit of what we have done. So in that way, I can tell you. Okay. So we don't have to expand anything. We don't have to use the combinatorial definition of A choose B, that it is that product by that. We don't have to use that. We will use this. So you know that if I take a polynomial fx, okay, where x is just a variable, okay, x is just a variable. Take a polynomial fx, and if you raise this to the power p, then this will be congruent to this mod p, meaning that the
Okay.
coefficients, yeah, this will come from the exercise which you have from the 2 exercises which you have done. Okay, I don't know if I gave you this, but it will come from those 2. So first of all, let me tell you this, that the coefficients of this are in fp. Okay, So this is in this. This is just the notation I'm using. You do not have to think like this. Okay. You can just think that fx has coefficients, okay, in integers, but taken modulo p, meaning that addition and everything will happen modulo p. Fine.
Thank you.
So, right. So basically the field operations on the coefficients are as is done in FP. So the field operations are done in FP and X is the variable. So in that way you can think, or if you're okay, you can think that. Then this is true. Okay. Why is this true? You may know this, but let me just do it right now. This will be combination of the theorems that you have done. So that's why this is actually in the spirit of, we will use this. This. Now, if I raise this to the power p, okay, then you have proved already that this is equal to this to the power p,
An minus 1 x to n minus 1 x to 3.
correct?
Yes, sir.
Right? This you have proved already. Yeah, you have proved for two terms, but you know that it is, yeah, it is, yeah, you know all that, yeah. This, and now you know also that an to the power p will again be an. Okay, because an is an FP, right?
Yes,
An, the calculations on an are being done modulo p. So an is
Yes.
treated in as an FP. X is not an FP, X is just a variable. Okay, X is just a variable.
Yes.
So this will become an and this will become this, right? And now I think you got it.
Yes, sir. It is x raised to 3.
Right, and so this will become f of x raised to p, right? Means f evaluated at xp. You can think of it like that, or correct, right? So then this was just a trivial calculation. It was just a calculation, and this is very important calculation because it's very nice, right? The coefficients are not changing, but the variable is changing. That is the beautiful thing. I mean, this has nice applications later on, and yeah. And you can also feel one thing that it seems more convenient to talk about that coefficients are in FP rather than saying again and again that we are doing modulo P and so on. Okay. Yeah. In fact, writing this is also incorrect in some way, but fine. This we have. Now this is your homework to this thing. One, show one using two. Okay, try to use two and show one. How will you use? Maybe there's to be some hint that is given. Basically, A choose B, right? A choose B is a coefficient of something. So you can sorry. Yeah, 1 second. I think let's do it now. I think something more is true. So yeah. Yeah, let us look at this. So let me not write homework. Yeah, let us look at this. Yeah. Whoa. Let us look at this. So you look at this. You look at this polynomial. Okay. And now in this one, what is the coefficient? So I'll say this is fx. Okay. Or just a minute. I don't know where I'm going. Yeah. Anyways, yeah. So you look at this. Now yes, right. So now in this, what is the coefficient of what is the coefficient of x to the mp in fx?
NP.
Sorry,
No,
NP choose MP, right?
yes, sir. Yes, sir.
Correct. That you know binomial theorem, right? NP NP choose MP, right? Right. Yeah. Now maybe yeah, I should say like this. Okay. Yeah, not in fx, but I mean, yeah, now I've changed the definition of fx. Yeah, so it's the same thing. Answer is the same. Okay. Now we know that fx to the p is equal to f of x to the p. Right? We know this, meaning that the coefficients are same. Right?
Yes, sir.
Meaning that the coefficients are same. Okay. So now what
Okay,
is the coefficient of x to the
1 plus.
mp in this? Am I correct? Yeah. Yeah, in this. Yeah. So what will be the coefficient of? I'm asking the same question, right? What's the coefficient of x to the mp in the same polynomial? But now we are looking at this version of the polynomial. They are the same polynomials, okay? But we are looking at this
So,
version, and
N plus M.
absolutely
N
right. This
choose.
is exactly. This is n choose m. Exactly, it's exactly n choose m, right? And so these two coefficients should be equal, right? But equal where? Equal in fp means equal modulo p, right?
Yes.
All these things, this is not equal. This is equal. I mean, this is equal modulo p. We are working in modulo p. There it is equal. Okay, yeah. So these two are equal, and so our theorem is proved. Do you agree? Okay.
Yes.
Okay. So this is the nice application. Like we did not need the definition of A choose B and so on, right? It is just that they are means we use a definition, but we used a more implicit definition. Okay. Right. So yeah, this is what I wanted to do. Yeah, I will have to stop today. Okay. Otherwise, I would usually
Okay.
have gone. Yeah, but today I'm a little constrained. Yeah. So we can, yeah, we can try to make it up, or yeah, you can count it as half class. That doesn't matter. Yeah. Next class will be Tuesday, 9:30 p.m. Okay, most probably. Okay, I mean, it means yeah, that's the timing. Yeah, unless if I change it. Yeah. So, were you there in last Tuesday's class? Yes, you were there.
Yes.
Yes, you were there, right? Yeah. So, what can I suggest you to do? Hmm. Yeah, it is fine. Yeah, matrices. Yeah, just keep doing matrices. We will just do some problem solving in matrices on Tuesday. Okay,
Okay.
right. And you keep reading Hoffman and Kuhn. So yeah, unfortunately, we are not able to discuss anything today from there. But this is what we discussed. Yeah, maybe I can give you some questions. No, leave it. I mean, it will be yeah. Okay then. Take care. Bye. Okay, I'll
I
meet you on
will
Tuesday.
complete. Okay.
Huh? Sorry.
Bye.
Okay. Bye.
Bye. I will